All right, let's go ahead and get started. I want to welcome you back to Unit 5, Chemical Bonding. We are on the 6th screencast for this particular unit, and we've got a little bit of cleanup to do. So let's finish this up, and then we'll move on to more complex geometric structures. So we were asking about the geometry of basic structures, and one of the questions that we want to look at is, what is the geometry of H2O? I want you to remember that water, or H2O, is the prototype for molecules that are what we call bent, right? So if we have water, it's going to look something like this. The lone pair on the electrons, or I should say the lone pairs are on the electrons, are what render this molecule bent. And water is just a very famous example of this particular geometry, so I want you to remember that one. The next one is, what is the geometry of BCl3? I want you to remember that boron is an exception to the octet rule, and therefore that means it doesn't require 8 electrons. This one's going to be trigonal planar. So when you see boron in the center, that's going to be trigonal planar. And that'll finish up our little quiz from last time, and we're ready to move on to some more complex structures in molecular geometry. So I want to take a look at this structure here. It's called the trigonal pyramidal geometry. Trigonal because there are 1, 2, 3 things around the central atom, right? But the question is, why is it not trigonal planar? In other words, last time we looked at BF3, boron trifluoride, and we said it was trigonal planar. What makes this different? What sets this one apart? Well, the answer is that by the way, let's just go ahead and refer to a compound that is a prototype for this particular molecular geometry, and that is NH3, otherwise known as ammonia. Let me write that, okay? So ammonia is a compound that has one thing in the middle, 3 things around it, just like boron trifluoride did, but there's a big difference here, and that is that the nitrogen in ammonia has a lone pair of electrons. And according to VSEPR theory, valence shell electron pair repulsion theory, those electrons are going to influence this molecule. It's going to push this part of the molecule down, or this atom down, this hydrogen here. It's going to push this one that way, and it's going to push that one that way. Let me make these little marks just like that. The point is this: the lone pair of electrons is important in dictating the shape of the molecule. The shape is influenced by that lone pair of electrons pushing electron densities here, here, and here down. So it's not going to be a trigonal planar situation, but instead it's going to be a trigonal pyramidal situation. It'll be a trigonal pyramidal situation. So there you go. Let's take a look now at trigonal bipyramidal. Trigonal bipyramidal, okay? So let's see. Here's what I want you to know. I want you to know that we have one thing in the middle, all right? And then I have 1, 2, 3 things kind of in the same plane. Then I have one thing up and one thing down, okay? One thing up and one thing down. A prototype for this particular molecule would be something like phosphorus pentachloride, PCl5, okay? PCl5. So trigonal bipyramidal, we have 3 things in the middle, one thing up and one thing down. That's the bi, by the way. So we have it kind of like, think of a pyramid on top, right? Think of a pyramid up on top of the plane and a pyramid on the bottom of the plane, and we would call that trigonal bipyramidal. Trigonal bipyramidal. All right, moving on with our shapes. The next one we're going to look at is this one. It's called octahedral. Octahedral. And an example or a prototype might be something like sulfur hexafluoride, SF6. Sulfur hexafluoride, by the way, is a very heavy gas. It's used sometimes for demonstration purposes because if you breathe it in, it will settle to the bottom of your lungs, and when you speak, it's going to make you sound like you've got a very, very deep voice, okay? So, sulfur hexafluoride, we've got sulfur in the middle, right? We've got sulfur in the middle, and we've got, so I'll put a sulfur right there, and we're going to have a fluorine here, a fluorine here, a fluorine here, and a fluorine here, and that kind of forms the plane. Then we'll have one up and one down. So sulfur hexafluoride is an example of an octahedral geometry. One thing in the middle and four things out in the plane, one thing up and one thing down. So a total of six things, six things surrounding, okay? All right. Now, by the way, why do we call it octahedral? I want you to, in your mind, kind of think of a four-sided pyramid on top, right, and a four-sided pyramid on bottom. We're going to be able to see this better in class when we actually use the little styrofoam spheres and the toothpicks. But for right now, I want you to kind of imagine two pyramids, one on top and one on bottom, and the two pyramids are going to have four sides each. Thus, 4 plus 4, of course, is 2, so that's octahedral. All right, let's move on. So we want to look now at one called T-shaped. It's called T-shaped for obvious reasons, right? For obvious reasons. We've got just kind of a line across, so there's something here, right? Some atom there, and if you just draw a line like that and a line like that, it's called a T-shape, just like that. Folks, don't worry about a prototype for this one. Don't worry about a specific molecule for this one. It's kind of, to be honest with you, it's not well known. I just wanted to introduce it to you, but I just don't want you to worry about a specific molecule. And also the seesaw geometry. For obvious reasons, folks, I don't know if you're old enough, to be honest with you, to know what a seesaw is, but I'll just tell you that a seesaw is a playground thing that used to be around when I was a kid. And one kid would sit right here. I'll draw a kid right there. And one kid would sit right there. And you would go up and down, and it was a lot of fun. But the point is that's called the seesaw geometry. Again, kind of an exotic geometry, one that you don't see very often. And I don't want you to worry too much about it. Just remember that I mentioned it, and I'm not even really concerned about a specific prototype for this particular geometry. All right? I just wanted to introduce it. Let's move on. Here we go. I want to talk about polar bonds versus nonpolar bonds. What do we mean by a polar bond, right? What do we mean by a polar bond? Well, what we mean is that it's not the same on one side or the other. Let's talk a little bit about nonpolar bonds to begin with. These have an electronegativity difference below 0.3. So somewhere between 0 and 0.3, if the electronegativity difference between the two atoms is somewhere between 0 and 0.3, we're talking about a nonpolar bond, right? We're talking about a nonpolar bond. So if I have two carbon atoms that are bonded, right, then the bond between them is going to be nonpolar. The electrons are being pulled by the carbon on the left just as hard as they're being pulled by the carbon on the right. In other words, it's symmetrical. When I say nonpolar, you should think symmetrical. You should think symmetrical. Now let's contrast that now with polar bonds. Polar bonds have an electronegativity of above 0.3 but below 1.7. We'll talk about what happens above 1.7 a little bit later. But for right now, I just want you to know that anywhere in between there, we're talking about a polar bond. Now one of the atoms is going to be more electronegative than the other. For example, if we have an oxygen-hydrogen bond as shown, the electrons are going to be pulled more towards the oxygen than towards the hydrogen. Because remember, oxygen is higher and to the right of the periodic table. It's going to have a greater electronegativity, right? And on the right-hand side, hydrogen is going to have a lower electronegativity. It's not going to be pulling those electrons as hard. So the electronegativity difference then between these two is somewhere between 0.3 and 1.7. We call that a polar bond. So that's a polar bond, but what do we mean by polar versus nonpolar molecules? So we can look at individual bonds, but what if we looked at entire molecules to try to determine whether they were polar or nonpolar? Well, a molecule can have polar bonds, but the molecule itself as a whole can be nonpolar if the bonds cancel each other out. You can have polar bonds, but the entire molecule be nonpolar if the bonds cancel each other out. Let's take a look at an example. Let's take a look at carbon dioxide. Now carbon dioxide has two polar bonds. If I draw the Lewis structure for those two polar bonds, it might look like something like this. Now these are double bonds on either side of this carbon, right? And there are also lone pairs of electrons here and here. I've just drawn the Lewis structure for carbon dioxide. Now let's take a look at the bond on the left. Let's take a look at the double bond that we see on this side. This double bond right here, that double bond is polar. It's polar because this oxygen is more electronegative than this carbon. This oxygen, I should say, on the left is more electronegative than the carbon on the right. Okay? So if I look at that bond, the one I've circled in blue, that bond is polar, right? It's polar. If I look at the other side of the molecule, if I look at that bond, remember this oxygen is also electronegative. So that bond is also polar. So what have I got here? I've got two polar bonds, two polar carbon-oxygen bonds. But what about the molecule as a whole? Well, as it turns out, the carbon-oxygen bond on this side is polar, and the carbon-oxygen bond on this side is polar, just like that. But they cancel each other out. And so the whole thing is nonpolar. So let's get that straight. You can have polar bonds in a nonpolar molecule. If you look at the kind of the electron clouds for carbon dioxide, it makes it readily apparent. This side of the molecule is polar. In other words, that bond, that carbon-oxygen bond, clearly polar. This side of the molecule, that bond, also polar. But they exactly balance each other out. So that means that the molecule as a whole is nonpolar. The molecule as a whole is symmetrical. Okay? The molecule as a whole is symmetrical, even though the two bonds that constitute it are nonpolar. Let's talk a little bit about carbon tetrafluoride. This one has 4 bonds. All right? Now this is another example of a situation in which each of the bonds is polar. Each of the bonds is polar, but the entire thing is nonpolar. And it's really going to require that you get out the styrofoam spheres and the toothpicks to convince yourself of this. But if I were to draw the polarity of this bond right here, carbon to fluorine, and draw this one right, that would be polar, right? That bond would be polar. So would that one. So would that one, and so would that one, just like that, right? The point is they cancel each other out. So even though each of the bonds is polar, the molecule as a whole is nonpolar. We're going to finish up with this water molecule right here. We have two polar molecules, right? We have I'll put the electronegativity arrow just like that towards the oxygen. That means that the oxygen-hydrogen bond is polar. I'm going to put another one just like that because that one is polar. So both of the bonds are polar, but they don't cancel each other out because this is not a linear molecule. There is a net polarity then. If I were to kind of add these two molecules up, there would be a net polarity in this direction, right? In that direction. So here we see an example in which both of the bonds are polar. The hydrogen-oxygen bonds, or oxygen-hydrogen bonds in both cases, obviously, are the same, and they're both polar. But the molecule overall is not symmetrical like it was for carbon dioxide, and therefore the molecule as a whole is also polar. Bonds are polar, molecule is polar. Folks, that's going to do it for this screencast, and that's going to do it for Unit 5, Chemical Bonds. See you on the next one. Thanks. Bye-bye.